So today we're going to look at inverse functions again, but we're going to look at them algebraically. So, and a little graphically. So here's a function, f of x equals 4x minus 5, which f of x is always the same as y. When we are trying to find the algebraic inverse, inverses switch input and output. So we are going to switch our x and y and then solve for y. So if x equals 4y minus 5, my first undo is to add 5. And then to get y alone, I would divide by 4. So I have my function, my inverse function is x plus 5 over 4, or 1/4 x plus 5/4. Now if I think about my graphs, 4x minus 5 has a y-intercept of -5 and a slope of 4. And I can draw a graph. And then my other equation is 1/4 x plus 5/4. So 5/4 is right about there, and I have a slope of 1/4, which is about that. And if I draw that graph, you can see more or less that they reflect over y equals x. In this case, 4x minus 5 is invertible because it is a function that is one-to-one. It passes the horizontal line test, and so does its inverse then passes the vertical line test. All right, here we're going to look at another one, and I'm going to sneak in a little parent function transformation review as we go. So if y equals x minus 1 squared plus 4, switch x and y, and now I have to undo in reverse order. So my first undo is to subtract the 4. The next undo is to square root, and hopefully you remember that when you square root, you must take plus or minus. So that gets rid of the square root. And my last step is plus or minus x minus 4 plus 1. And so my f inverse of x is plus or minus x minus 4 plus 1. If I try and graph the original function, this hopefully recognizes a transformation of x squared. We've shifted to the right 1 and up 4, which is going to put that vertex right at 1/4, and I have a y-intercept of 5, and when x is 2, I get this. All right, now right here, we should know that this is not invertible because it fails horizontal line test. There are some y's which give me more than one x. And how is that going to play out? Well, when I try and graph my inverse, again, we can use parent function transformations, or we can sort of graph points. 1/4 becomes 4/1. 4 or 0/5 becomes 5/0, or becomes 5/2, right? And we have this and this. So that is the inverse relation. You could also think of this as being transformations of square root. We've shifted right 4, up 1. There's my square root function, and then when I do the minus, it's the bottom part. For a challenge for tomorrow, I want you to think about, can I restrict the domain on f so that I get an invertible function? And then what does that do to my inverse? So think about that if you want. Come tomorrow, we can talk about it. One last inverse problem quickly. So here we're going to switch our x and y. This is going to be the trickiest that we do. I need to get all my y's together on one side so that I can solve for y. I need to isolate y. They're together here, but I'm dividing. I never like dividing by what I'm trying to solve for. So I need to get y out of the bottom. And the best way to do that is to multiply both sides by y, because now I really have 1 here. I have y plus 2 multiplied by something and divided by the same thing, so I have y plus 2 on this side, and if I distribute over here, I get 3xy minus 4x. So far, so good. I need all my y pieces together. So I think of this as being 4 different chunks. Those 2 chunks have y's. I can move either one to the other side. I think it's easiest to move this guy over. So to do that, I would subtract y from both sides. And now I want to get any piece that does not have a y away from that side. So I'm going to add 4x to both sides. Now I need to get y alone. So these things both have a y. I am going to distribute out that y, factor it out. And what's left is 3x minus 1. Hopefully you can see that if you distributed in, you'd get 3xy minus y. And I do that distributing out so that now to get y alone, I have to break this connection right here. Y is multiplied by the quantity 3x minus 1. So to get y alone, I divide both sides by 3x minus 1. And that's my f inverse of x. That's about as tricky as we're going to get. One last thing we want to look at is what happens when we add composition into this. So if you take the composition of a function and its inverse, so f of f inverse of x or f inverse of f of x. Well, let's look at one quick example. So if f of x is 4x plus 3, f inverse, so if x is 4y plus 3, I subtract 3, divide by 4. So here's my inverse. Okay. If I take this and I put it in there, so I'm going to have 4 times x minus 3 over 4 plus 3. These guys are going to cancel, and I get x minus 3 plus 3, and I get x, which is kind of curious. If I go the other way and I take this and I put it in there, I get 4x plus 3 minus 3 over 4, which becomes 4x over 4, and also x. Curiouser and curiouser. Well, if you think about it, if I take x and I put it into f, out comes f of x. If I take that f of x and I put it into f inverse, where should I end up? Back at x. Put x in, do something to it, undo it, you should end up back at x. And that turns out to be true. F of f inverse of x is always x, and so is f inverse of f of x. There may be some domain restrictions that do some weird things, but overall, that's true. And this method is a good way to check if your inverse actually is the inverse. All right, so here's a couple problems for you to try on your own. Bring them your answers tomorrow and we'll check in.